So I'm going to show you a strategy that I saw being played around here. I think most of you found this out fairly quickly, like a few times playing, because if you did lose as the first player the first few times, you thought, well, I'm not going to let that happen again. So I think that's the attitude you have to take on to start seeing the strategy. So when you play, so when I first played, I wanted to keep my things neat because I like playing Tetris and seeing it neat and all the things go down. So I was putting my elements in the corners. That's not a good idea, actually. So when you play, you focus on where you can place your domino in the context of a square like this. So you're looking at these square pieces and saying, okay, if I have something like this, where an empty square and this, and these are my only two openings that I see on the board right now, or I have openings like this on the board right now, you could put your vertical piece, if you're a vertical player, you could put it right there. And that would block the ability for a horizontal piece to go right here. So you're, in fact, when you put it there, you're blocking the other person. The opponent would then do this, and then you're done. So that wasn't a good strategy, actually. But on the other hand, if you had those same two squares, you could put your vertical piece here, then they would have to do this, and you win, because they can't move anymore, if these were the last two types of squares left over. So it's almost like you are going backward and backwards. This is called backward induction, by the way. I know you have heard the word induction. It's backward induction. You have to think a few moves out and then go backwards from that. Down with your opponent. In fact, what we realized a little further into this game, so when my daughter started playing it, that one of the strategies you can employ is you're really trying to block the other person from putting their thing down, and you also want to leave yourself a get out of jail, right? So if I do this as my first option, now I've left myself something down here that vertical can't use. So my idea of putting them neatly into corners, I found out quickly. I ended up losing. So you don't want to put them neatly into corners. But the vertical can take the same strategy. The vertical puts it right here. Then now I can't put my horizontal here, and they've saved themselves a space at the end, right? Then I'm going to go and start doing this all over the place, like so. So somebody had mentioned don't put them neat. If you try to put them neat, then you end up losing. So this is you have a messy looking thing right away that looks something like this. So this seemed to be the optimal starting point to start blocking out the other person and making sure you had get out of jail cards. And when we started playing like this, the first player was always winning. So now that's what I call a conjecture. I conjecture that if I use this strategy and I'm the first person to go, which I wasn't because she got to go first, but that I will win. So I'm going to give you some formal definitions now, a little bit back to boring. A combinatorial game, I gave you the intuitive definition. The way they define it in the book, they define it as being two-player games. Two players take turns, moving alternately, and the play continues until the player whose turn it is has run out of legal moves. So you just played a combinatorial game. Why this is important is because if two players are playing a game in this way until one person can't move anymore, there's only a finite number of moves. So you can start counting different possibilities. So it's really possible to list out all possibilities and then pick the optimal route. And that's what makes it fun for mathematicians who like to play games. A combinatorial game has no chance. There's no devices like dice, spinners, or card deals. That's a different class. You already took it because it's a prereq. That changes things. Sometimes we've taken games that we've done research on, like I think if you look on my CV, you'll see games with NIM, and added a probabilistic element to it. It makes it more fun. So when we're done and exhausted with the regular combinatorial game, we start doing things like that to expand it. Each player, when you start analyzing this mathematically, each player knows fully the details of the game and where they are. So it's not like something's hidden from them. In some games, you're hidden and you have to kind of do a chance move. In this case, you don't. You're looking at the board, you know what the layout is, you should know what you should do next. That configuration is called the game state. I'm not sure if you had differential equation and they talked about state variables. It's a very similar idea. It's the state of the system in that point. All of this ensures that the game ends in a finite number of moves. So here's another question I could ask you that's mathematical about the game you just played. What's the minimum number of moves it takes to win the game? It's a math question. I keep forgetting to look on my cell phone to see if there's an app. Then you can sit around and play this all the time. I know I have a cell phone policy, but I don't think everybody has a cell phone policy. And if they say anything, you say, I'm doing my homework for my other class. Don't say my name. If you had me before, I always say, blame it on Dr. Song. Dr. Song told me to do it. Normal play, I guess that's what you saw in the little normal play. Normal play means the last player that has a legal move is declared the winner. You can change that and say that the last person that moves is the last person that, or the first person that doesn't have a legal move is the winner. That's called misery play. Or that the winner, so it flips it around. All the ideas that are presented in this class can be expanded to extensions, and you'll see them when you start doing literature searches. You'll see that sometimes the open problems come when someone's taken something that's been very fun to play with here and then extended it to checkers or dots and boxes, which are not following this format. So this format that you get, although it's really restrictive, it does lay a foundation for you to fool around with other things. Classical game theory, which is the game theory, did I move on too fast? Yeah. The game theory that you hear about comes from economics and Nash's equilibrium, those kind of things. Those are a different set of game. That's classical game theory. This is combinatorial game theory. So it's a little bit different than but it's all in the same, it's the same group of people. You go to the conferences, same group of people. Actually, we should have Steve Brams come and speak here. I don't know if he's still speaking, but he's extended this to even fair division of property among divorces. So he can give a really nice talk about how game theory is extended to fair division. It's not too far away from that, an idea of where two people are playing a game, they're dividing their property, and both of them want to in a situation where they're dividing the property in a way they feel they got their fair share. So it's not that far of a jump. He's a political scientist, and he's been paid a lot of money for coming at divorces and splitting up the property and merging companies and unmerging companies, both of them. And I guess in my day, we always called it player one, player two. Player one would go first, player two would go second. But your book is using left and right player. And I mentioned this because I've been doing this for a long time, and I might switch back and say player one, player two. But they talk about the left and right player, and I think what they mean is the board is set up in between two people, and there's a left player and a right player, and the left player would go first. They also mentioned some other things like the Alice and Bob. That's pretty typical, where A would go first and B would go second. And they have a whole list, and that's on page 4 of your book, of different ways they designate the players. the game pieces may have colors, like we had black and white here, and you might need 3 pieces, so you could have black, white, and gray, and they mention that in the book, that you might have other things in there. And I think if they have anything else. I think these are the highlights. As we come upon each game, you'll see it changing. She in pre-cal? Yeah, this is room 222. Math 222 is not as fun. You should have said, look, sit down and play this game with me, and if you win, I'll tell you. When they talk about left options and right options, they mean the set of possible moves from the left or the right for whoever's playing. So what could, I mean, you were doing that when you're playing your game, right? If you were the vertical, you were thinking, what could I do? And what are my possibilities? It was kind of like the 2 squares that I had at the end where you're looking at, what are my possibilities? Oh, I don't think I'll do that one. I'll do this one. So the whole set of possibilities is called the left options or the right options. And unfortunately, you didn't take a combinatorics class. Did you guys take graph theory? Graph theory? No? Okay, we do a lot of listing of possibilities in terms of trees. You did it as in probability, right? You listed out the possibilities and then you counted. Okay, so you can list out the game possibilities also in terms of a tree. And this you can't copy from the notes because it's in your book and I did a screenshot of it. You can try. So I was confused for a minute. I mean, it's just a listing. So they show you pictures of listing. If you were looking at the pictures, they don't have a good caption and they don't have a good description on top of it. But what they mean is, what are all the possibilities for the vertical in this situation, right? If I have these two pieces, it's not looking at what happens with the horizontal. It's just saying, where can I put that vertical piece? Here, they're looking at all possibilities of what can happen next. If I have these 2 boxes and the horizontal's here, then this could happen next, or this could happen. You could end up, you know, these are just 2 pieces on your board. There's other things going on. So you could end up seeing it filled this way or seeing it filled this way. If this happened, then they don't have the next arrow down. And if this happened, they just didn't show it to you. But this is how you build the tree. So you're looking at all the possible configurations that you could see in the end. You could also have trees written down like this. You were doing it in your head. If I do this, she'll do this, and I do this, and she'll do this, and then, right? So you were doing it in your head. But you could actually list it out, scratch it out on a piece of paper and see what happens. Or you could say, okay, if I have this, then the possibilities that could get filled is this way, and the other set of possibilities could be filled this way. I don't know if you drew binary trees in probability, we had coin flipping. So if I did this first and then did this and you do the tree, it's very similar. It's exactly the same. It's not very similar. And this is the third move. So these pictures there's more pictures in your book. So you get the idea. We'll be drawing a lot of these in class itself so it's the easiest way to map out a strategy. You draw all the possibilities and say, I'm going to take that path. We're not going to do this because we've actually run out of time. Cram is the same game that you just played, but there's no you could go vertical or horizontal, both players. So it changes everything. And what time are we at? Huh? I think we can start at least doing number 1 on the exercises on page 7. And if you don't have your book, it's on the web, PDF. I just looked up PDF lessons in play and I found it.
Thank you.
I didn't know that either. I ordered the book, and the only reason I looked online is they haven't sent it to me.
Is it on Canvas? The PDF?
I can put it there.
Yeah, which is No, but I